Here is the next example. Here we have a combination circuit with series parallel combination of resistors, inductors, and capacitors. Okay. So first thing, the given circuit is in time domain. How do I know it's time domain? I can clearly see, this is in Henry, not in ohms. So, but here, is this RMS value or maximum value? That's always RMS value until unless I specify it. Okay, we'll take that as RMS. Now everything we're going to convert this into ohms. So that's L1, L2, and C. Okay, so JXL1 equal to J omega L1. What is omega? Frequency is given, so omega is 2 pi f, which is 377 in this case. So J377 times 1, which is J377 ohm. JXL2, J omega L2. So J377 times 0.5, which will end up with J188.5 ohm. Minus JXC equal to minus J over omega C, which is minus J over 10 micro times 377. That value is minus J 265.25 ohm. Okay. Now, as I said, always start from the element which is far away from the source. So look at this capacitor. Now we call this as capacitor reactance because this is in ohms. Okay, minus J 265.25 ohm. So this capacitor reactance is in series with 100 ohms. Now, so let me label this as Z1. So Z1 equal to 100 minus J 265.25 ohm. Same thing here. This resistor 2 is in series with the inductive reactance. I'm going to call that as Z2. Z2 equal to 100 minus J 188.5 ohm. Now, these two are in parallel. Even if I take this as Z3 here, so if I label this, simplify this, Z3, Z2, and Z1. So this is Z1, this is Z2. We can clearly see these two are in parallel. So Z1 parallel with Z2, which equal to, I'm going to label that as Z4. So 100 which equal to Z1 times Z2 over Z1 plus Z2. It's just like resistor. Okay, once everything is in frequency domain, impedance is nothing but a resistance in ohms, but with complex number. Okay, it's a complex number. So this value 100 minus J 265.25. So here we are dealing with the complex numbers, so that's a little bit difficult part. We may need to convert them into polar form, rectangular form, polar form, rectangular form many times. 100 minus J 265.25 times or plus 100 minus J. Isn't it plus J or Z2? See, silly mistake. I always does that. Okay, 100 plus J 188.5. Okay, now the numerator must be multiplied, denominator must be add. We will end up with I'm going to, for multiplication, I'm going to convert them into polar format. When I convert them into polar format, that's 283.47 at an angle of minus 69.3. Another one is 213.38 at an angle of minus plus 62.05. The denominator I'm going to have 214.22 at an angle of minus 21.1. Okay, this is my Z4. Okay, now we need to multiply these two numbers, add the angles. Okay, when I multiply and then divided by 214, so basically this is going to be 283.47 times 213.38 divided by 214.22 at an angle of, the numerator we're going to add them, minus 69.3 plus 62.05. Denominator we subtracted, minus 21.1. Okay, after solving this, I end up with 282.35 at an angle of 13.8. That is 274.1 plus j 67.3 ohm. That's my, this is not Z total, this is basically Z4. Okay, now Z total equal to Z3 plus Z4. What do we have? Z3, 200 plus j 377. 200 plus j 377 plus Z4 is 274.1 plus j 67.3. Okay, so the total is 474.1 plus j 458.63. Okay, you might find small errors here and there in my numbers. Don't worry too much about that. So when I convert this into polar format, 649.79 at an angle of 43.13. So I total equal to V over Z total. V we have 120 at an angle of 0. Z total is 649.79 at an angle of 43.13. Okay, now this current is 0.1847 at an angle of minus 43.14 degrees ampere. That's the current passing through the circuit or supplied by the source. I didn't ask you current passing through each element. Here, similar to the current division rule or DC circuits, we can use the current division rule, voltage division rule to find the individual currents. Okay, I'm going to stop it here. Thank you.